we're just really delighted to have Dr. Oliver Smithies here. He's an interesting person to talk to, whether you're talking about gene targeting or flying or any of his other interests. And so you always have a great way of putting what you're doing into a context, I think, that's meaningful to all the rest of us, whether we're in your discipline or not. So thank you so much for coming and sharing some time with us today. And we're also really pleased to have Tony Waldrop here to play the role of moderator and chief conversationalist. I didn't tell you that was part of the role, but I'm sure that'll come easily to you. Of course, Dr. Smithies is world-renowned as a Nobel Prize recipient in 2007. He's been a eminent, let's see, I have to read this right, excellence professor of pathology and laboratory medicine here at UNC since 1988, has published over 300 recent articles and won numerous honors and prizes on his way to receiving the Nobel Prize in Physiology or Medicine in 2007. And if you haven't had a chance to look at any of the clips of his Nobel acceptance speech or his lecture, I really recommend that you do that. They're very entertaining. There are various ways to get to those, one of which is from our own library's website, so dip into that and enjoy it, as I'm sure you will. Tony Waldrop is also world-renowned in his own way, having won the world record for the indoor mile in the mid-1970s, we'll say.
Yeah, let's not say how long.
We won't say exactly, mid-1970s. And then gave that up to pursue a career in science, so aren't we glad about that? Tony rejoined us, being a North Carolina native son, in 2001 as Vice Chancellor for Research and Economic Development. So Tony and Oliver are friends and colleagues and speak the same language, although in slightly different disciplines, and so we're just really looking forward to what you have to share with us today. And those of us who are in the library and information business in this room have a particular interest in hearing what you have to say. We know that so many things have changed in science and in information in the last decade or so that we think it's really important for us to be able to understand how those changes are impacting the way science is done, such as I'm looking with great interest at the various formats of information that you have displayed on the table here, and that's definitely one of those changes. So we know that we have a lot to learn from hearing your comments and observations, and hope that it will be an interactive session. So let's get going.
Well, let me just say what an honor it is to be able to set up here with Oliver Smithies. As Carol introduced him, he certainly is world-renowned, was world-renowned long before the Nobel Prize, but even more so now. The thing that most impresses me about him is obviously the science that he's done and the impact that he's had on his field, but that he is such a genuinely nice individual, and he is so willing to go and talk with whatever group that might seek to have him in front of them. I know that he's here today. I believe you have an interaction with a high school later this week or next week one, and I would encourage you when we get to the point of taking questions, and in particular the students, to ask whatever question you might have. I would second what Carol said as far as going and looking at his Nobel address. He specifically addresses students in that. And Oliver, I watched that clip on the web and saw you looking up in the balcony where a lot of the students must have been, and so it was important. It's also amazing, those of you who have heard him talk before, to get his perspective of how things have changed over time. And he's going to share some of that with us today. And Oliver, if we could just get started by you talking some about record keeping and data preservation and how that has changed over your career. And I know some of the props will enter into that discussion. So let me turn it over to you.
Well, I think maybe I'll start at the level that the students will recognize how you learn something.
Great.
I was very lucky, and I'm fortunate, perhaps is a better word to use, to have been a student in Oxford University. I was a scholar. There was various levels of scholastic fame, as it were. You were a scholar, or you were an exhibitioner, or you were a student. And I was a scholar, which meant I won a scholarship from a small town in the north of England, where I went to school as in the early days until I was 11 at a little village school that is still there. But the way of teaching in Oxford is a very good way, and I think it's something I've tried to use later on in universities here in the United States. And primarily the teaching is done through reading the original literature. That's to say, you're given a topic to write a weekly essay on by your tutor, who may be a man or a woman, depends, just the tutor associated with your college. And it might be very vague. It might be a topic like, write me an essay on pain. That's all you were told. And now you've got to go and read about pain, and so you can spend maybe a day reading the textbooks and maybe a couple of days reading reviews, and then after that you were expected to go and read the original literature. That's to say, by the original literature I mean the primary publications. And it was always rather frustrating that you had to go to the library and look for the journal that you wanted and look for the particular issue, and the chances are somebody else had it out anyway, and then you would have to go back. And so there was a continuous sort of fight about finding where books were and so on. But nonetheless, that method of teaching, of getting people to read the original work, is vital, I think, to real scholastic ability and understanding a subject. If you read only what has been distilled by somebody else, you don't have to go through the process of extracting the important information. And it's interesting to me that if you go back to the very first publications on various topics, you often find that they're quite simple. That, for example, the one I was thinking of that I showed the other day when talking to some students in not Central University, but anyway, in the National Institutes of Science, which is a collection of colleges, of historically black colleges, a society associated with them. And I was talking to them about sickle cell anemia, because of course that's something that concerns black kids. And I showed them the original paper, and it was 1910, and anybody could understand it. In slightly garbled language, it says, the peculiar sickle cell-shaped erythrocytes in a person with anemia. And that really is the whole of the message of that paper. And any person can get that message, and you can get the excitement by going back to that, of understanding what was going through the mind of the person who first saw that. And as you go through the different parts of science, you can find that true of many. For example, I mean, all of you know about Watson and Crick. How many of you have read his original paper? 2 of you, 3 maybe. You know, that paper is only 1 page long. Only 1 page. And you can read it, and it's not difficult to read, and out of it you can extract what was their genius, because they were genii, if that's the right plural for genius, because they recognized how the different parts of DNA fit together, They published it as a double helix, which it was, but that really wasn't important. The important part was learning that basis paired, and that's in 2 sentences in that paper, and you can read it and you can understand it. They were not very modest men. One of them is still alive, the other is not. I've known both of them, and because they ended up, and I always think this ought to be said in a snooty accent, it has not escaped our notice that our model will explain the replication of DNA, or words to that effect. And that's all they said about it, and it's a throwaway sentence showing what it is, but it's so enjoyable to go and read that in the original. Now, you can't do that easily with the ordinary sort of library, but you can now, you see, because you can go on PubMed or other forms of even Google, and you can be directed to original literature, and you can get a PDF that you can read of the actual words and the actual paper that is describing something of interest to you. And in that way you can learn a lot more, a lot faster than it used to be possible. And I was thinking about my own experience of learning in this respect, and about a couple of years ago I had an idea about how the kidney might work, and I'd never studied the kidney particularly, and I hadn't any training in that area. But you know, in 3 months you could get yourself completely immersed in that topic, because you could work your way back through the literature. It isn't yet good enough to go all the way back, but it's getting better all the time, and I think library scientists have to think about that particularly, about it's an opportunity for all of us to read all of the literature, not just the last 2 years. Or the last, it used to be, maybe it got better with PubMed, went back about 6 years, 10 years, and now you can get back much further. So that's a very important thing. But we have to teach people how to use that information. They shouldn't just go and skim the current PowerPoint presentation of what it is. We should teach to go back, because it's in the fine print that you really understand what's going on. It's not in the title of a paper is the grossest exaggeration that the authors could get away with. And the abstract tries not to say any of the problems. And then you have to read in the paper, and then you can maybe deduce, etc., etc. So anyway, well, how do you handle all that information? Well, there's a storage system up here. It's plant senescence in it. It won't last more than, well, I don't know, maybe if some people are lucky it lasts 80 years. Mine has lasted 80 years, and it's still going, but it won't last forever. So we have to get that information down somewhere. And I thought it was interesting to look at how that was. And so I brought some of the things that were in my history, as it were. And this was a pretty important part of the storage system at one stage of my life. And I don't know how many of you recognize it, but it's a teletype tape. And my first computer program was written with a teletype using a time-sharing computer that was 60 miles away. Our university in Wisconsin didn't have a time-sharing computer, but there was one that General Electric had in Milwaukee, about 60 miles away, and you could communicate with them with teletype. So it really was good interaction. You could actually get an answer within reasonable time, instead of feeding cards into an IBM computer and going back next day and finding, as Nvoya has told me that used to happen to her, I'm finding a mistake on the first card. And so all the rest were useless. So that's a big advance. But you can't read this anymore. I don't think there's anybody has a piece of equipment amongst us who could read it. And then it got a bit better because it went into this sort of thing, you know. And this was a fairly advanced one, you see. And so that was computer memory. I can't read this. So, okay, what's going on then now? Who has a floppy disk? Who has any floppy disks anymore? Well, you have a few. Can you read them? You can't read them anymore. These were the greatest thing, you know. You're going to have all of your knowledge and all of your information on these things. It got a bit better. Then it got to these, didn't it? These are the CDs, and I don't think those are. It's getting so fewer and fewer computers can even read these. And well, what about these? Oh, they're the cat's whiskers. They'll be out. 10 years from now, you won't be able to read this. You won't have a machine that will read it. It will use something like this. Because this one, and even this will be out of date, and this one is now this particular one is 2 gigabytes of information. 2 gigabytes. I don't even remember how many zeros there are to get to a gigabyte. So they're all going to go out of date, is my message to you. So how are you going to have a record that you can still use for a long time? And I think you have to still think about the old method of pen and ink, or paper anyway. And I realized I could exemplify it by this, and it goes also into library science, because this says OS planning notes, and the date on it is 1953, so that's 55 years old. And you can see how I had to learn at that time, because it goes through chemical abstracts and quarterly cumulative medical index. That's all you could use. That was already, it was a library tool, because you could go to the library and you could get this big book, but these big books, there were many of them, which were chemical abstracts, and you could get this quarterly, as it obviously is quarterly, cumulative medical index. And my first job was, I was hired by a grand person, David Scott, and he was, as I thought at the time, rather ancient. I think I would think he was rather young now, but anyway, he had been one of the people working in the early days of insulin. Insulin was discovered, as some of you know, in Toronto in the 1920s by Banting and Best. And David Scott crystallized insulin, it's a protein, and crystallized it in the form of zinc insulin. And it was very slowly dissolving, and it's still used to this day as a slow-release insulin. And so when I went to ask him for a job, he said, well, you can work on anything you like, Dr. Smithies, as long as it has something to do with insulin. So you see, my note says, quotes, insulin. So that was the scanning that I was looking at, all of the articles which had insulin in them. And you can see, if you can read, this is, in 1945, I found 2144 superscript 4, P1023 superscript 4. I have no idea what the superscripts mean. But most of those are crossed out. And then about the fifth down is 1430 superscript 7 with a check mark on it. And this has now got the title written in it. Statistics of assay, extended crossover design and its use in insulin assays. K.W. Smith et al. Quarterly Journal pharmacology, etc., 1944. So you see now I've got a reference, but it goes on all the way through these, and you can see that some of them I even wrote out a bit more. Here I've got one, and it sort of gives the abstract, and there's pages and pages of this stuff. And that's what you had to do to try to find your way around. But how many of you would be able to produce a record that's 55 years old that shows you what had happened? Only by writing it on something that will last. And so it's interesting because it actually goes into, it runs immediately into this which is falling apart, you see. But this is my lab record book from my first job. And it starts with Old Smithies, room 327, School of Hygiene building, College Street, Toronto, October 1953. You see, so it follows directly from that. And in here you'll find me trying to work with insulin. And there's a page which I used in my Nobel lecture that shows that I was having trouble with it, etc. But here's a record, isn't it? And it still exists. And it's 50-odd years old, and you can go on, and then you can trace, and you can see this one, and this one I like because this was the first time I found a genetic difference in anybody. That was a difference in the serum proteins. I thought it was a male-female difference because this was the first female I'd looked at, but it wasn't. It was inherited, but there it is, and it's drawn in there because it didn't have a camera. So I couldn't have recorded it any other way. But anyway, it goes on like that. And then I think this is an interesting one because this is now much more recent. And this one's now in 1982. And this page has my first ideas on how to do gene targeting. And it's all on this one page, you see. And you can still see it. So you can see, and you can look back and you can see what was going on in Smithies' head before. The page before has nothing to do with it. It's a new thought, and what happens then, and what you have to do, and so on, and maybe, and then here, 3 years later, is one. Still, you see, I still enjoy them. 3 years, 3 years later is the time when it worked. 3 years and 1 month. C gamma 13, because that was gamma, the book Gamma, and I'd gone through the alpha. I'd gone through the Roman numerals up to about 30. I'd gone through the capital letters, gone through the small letters, gone through the Greek letters, and then I'm now back on the ordinary letters with prime numbers. So I can use primes, and so on. It goes on, and then what's this one? Well, this one says Monday, March the 30th. What day is it today? Monday, March the 30th. DTT to GSH injection. And it checks for 1 milliliter of gold chloride, 4 milliliters of distilled water, 3.8 milliliters of water containing 25 milligrams of DTT. And so it's my notebook still. And then somebody could, and that was 9:52 a.m. And I was trying to do the experiment in a timed manner. And at 10 a.m. I gave this fraction injected by Mike. That's my postdoc, and we're going to see if making the things fast will work. But these records are very critical. So somehow you people in information science have to bridge the gap between these which won't last and these which will last. And you've got to teach people to use both, not just one. And I think that's an important thought, because, you know, otherwise you're going to have happen what have happened here, you see. This is the last, well, actually one before the last, because I've saved the last issue of Christian Science Monitor in this form. It will not be available in paper form anymore. And this is our local newspaper. It's the nice one. It's talking about the Blue Devils coming up short. So it's a very good page, but you see, it's already shrunk into nothingness, hasn't it? And this won't, I'll bet you 2 years from now you won't get this anymore. So that's the problem of information science that you have to think about. Okay, well, I've spoken enough now, so somebody else can talk.
Not nearly enough, but I have a few questions, and then certainly I know others do. Oliver, we talked some prior to starting today about how your use of the library has changed over time and changes that have been made in the library. Would you be willing to say a few things about what it was like when you started?
Well, yes, I told you about what you had to do as students, and then occasionally you would, and so you'd read a lot of things, and occasionally you might even, there was one that I thought was marvelous, when in this lecture, actually this essay on pain, because I came across the fact that somebody had had the idea that there'd been a protopathic organism which could detect pain and not much else, and an epicritic organism which could distinguish all sorts of fine things, and that this is the way evolution had gone. And I learned one sentence. I thought it was marvelous because it was one sentence, and it goes, talking about the protopathic animal. This creature, if it could propagate its bewildered kind, which appears doubtful, could have little survival value, for in response to a stimulus which it could not understand, from a stimulating agent whose nature it had no means of determining, could only respond by curling up and micturating, which, for those who don't know, is peeing. But that's in this form of memory. But anyway, that was.
So you've had a long interest in the kidney, all the way back to that.
Yeah. But anyway, I mentioned going to the library, and the library has. It's always been a critical part of scholastic endeavors, and I'm sure we go back to the famous libraries that you can find all over the world, and that tells us how important they've been. But the library is a practical tool in a sense, and then you have to learn how to use it. And initially it was go to the library and look for the journals. Then it was helped by cumulative index. And then, as you think, PubMed was an enormous advance, because then you could have the title and you could have an abstract, and at least you could know which one was worth going to look for. You couldn't see the whole thing yet. You would have to go to the library to see the whole thing. But you would know what you were going to look for, so that would help a lot. And now, as I say, we can do much better than that, because, well, perhaps about a third to 2/3 of the papers that you want to read, there is a full copy available. Not far back yet. And the search engine for PubMed is a very poor search engine, in my opinion. In fact, I don't think there is a really good library search engine, because there's one for chemicals called SciFinder, and that helps you with the chemical literature, but they're really rather poor. And I can exemplify that, and some of you can. I'm sure that you have a reference in front of you, and you search with the terms in that reference, and it doesn't come up. So that tells you that they are not adequate yet. But they're improving so much, and you can learn so much faster. I have to tell you another anecdote. Well, it's a true story. It's not an anecdote. It's what happened. About a year ago now, they had an affair in New York where they unveiled some places where the Nobel Laureates' names were inscribed, and it was associated with the Swedish Embassy. And the Swedish Embassy or the Nobel Foundation, I don't remember which, had asked students to write an essay about some topic of their own choosing and submit it in a competition. And a young woman, I would say a girl really, she was only 16, won this competition for an essay on Niels Bohr. And I got to read her essay. And it was almost exactly the same essay that I'd written when I was 23, when my topic for the week was discuss the Pauli exclusion principle and the periodic table. That was your essay. And the Pauli exclusion principle is to do with quantum numbers that electrons can have, and that you can't have two electrons with the same quantum numbers, etc. And this led to a marvelous understanding of the periodic table. And so I said, I wonder if this girl now, is she a lot smarter than I was? Or what? And then I came to the conclusion that we were about equal, and that it was now a lot easier to learn, so you could learn sooner. And that the difference was that she could get this information at an earlier age, and that we were probably equal in that respect. I might add another story about that essay, because I had a glorious time writing it, and she had with hers. We both enjoyed the topic so much. It's a glorious topic, and it seems very sophisticated, and it isn't really. But anyway, I got about halfway down the first page. I had 12 pages reading this to my tutor, and he found something that I couldn't justify, and I didn't really understand. And the rest of that tutorial, they lasted about an hour, was teaching you that you never ever write down something that you don't understand and that you can't justify. Mm-hmm. A marvelous lesson. But anyway, going back to this topic of the library, you can see what I'm saying. It's a lot easier now. There's a lot more information, but it's a lot easier to get it. There's no excuse for not going back in the literature anymore.
Absolutely. So something that libraries have pushed for, and something we're seeing throughout the country now, is the open sharing of data as soon as it's put into publications. And I wonder if you might talk some about what impact that's had on science over the years, the availability of being able to do this rapidly.
On my information of science, it's not done well, is the simple answer. It's not really practical to put data directly into a computer, at least our sort of data, because it's not in a handleable form, and you have to hire a person who tries to put it into a handleable form, and by then it's become passé or whatever, and it's not really terribly useful, I don't think, at the moment, in the form we've been exposed to. I suppose that's partly showing my age, but I haven't found it helpful.
But if you go to the next step and look at papers once they're accepted for publication.
That's a different matter, because then it's already been digested and it's in a form you can read, and then the supplementary material particularly is extremely valuable, because that can have all of the primary data, or a much bigger proportion of the primary data. Those are absolutely invaluable. That's completely different from this putting in data as you raw data. It's not much use to people in most of the situations, because it's too personal, most of it. I mean, the method of writing it down, or the experiment, and it takes too much time to do it.
Some people have pushed back some on open access, and they've worried that if the articles are published too soon, other people will get their ideas and be able to quickly replicate those before publication. There are many of us who don't accept that, but I'd be interested to hear from you as far as your thoughts.
Well, I've always thought that anybody who came into my lab could hear what I'm doing and could hear what I'm thinking. I mean, that's part of science, and I'll take the chance that they'll steal it. I mean, I think one time 9 times out of 10, you will have great enjoyment in talking to other people and just communicating freely. Maybe 1 time in 10 you might be burned a little bit. But I think it's even less than that. And if you cut off that, you've thrown away 9/10 of your enjoyment. It isn't worth it. It isn't worth being secretive about things. But I realise that that's an ivory tower sort of view, because if you're in a commercial operation and you have to patent something, you obviously can't go around talking about it all the time. I've never had difficulty in what you would call competitive science. I've always try to avoid it. If I've got in that situation, I've tried to get out of that field of endeavour. It's not pleasant. I don't enjoy it particularly. I've won competitions of that type, and then I've been glad to leave it. There was one that occurred while I was here, and that was at the time cystic fibrosis gene was first identified. There was a lot of competition in trying to be the first to knock that gene out. It wasn't very pleasant. And Bev Kohler, who's a professor here now, and she and I both agreed that it wasn't really a pleasant time for us with that sort of competitive atmosphere. And though we, in a sense, won the competition because we got the first one, but we neither of us enjoyed it much, and glad to be out of it. And so it's not the way to do science.
And I agree with you very much. An additional part of sharing of the information is that not only has it made it easier for students to learn and for scientists to share information, but I think the general public also has a thirst for getting information sooner than what we used to see before. And I'd be interested to hear your thoughts about that and how important it is to get that information out to the lay public.
Well, I think it's a duty of scientists to make sure that the people who are, after all, funding them, the ordinary public is paying for the science which we do, that we can talk to people about it. And I don't know what the best way to do it is. I've been trying to do my little bit, as it were, since the Nobel Prize was awarded, because people want to hear me talk. I don't talk any better than I did before or any more wisely than I did before. But for some reason people want to hear it now. But it is a challenge, and an enjoyable challenge, to talk to people so that they can understand. And I found that business of I'm talking about original papers. I will go and talk to a lay audience, and I will use the original papers and show them that they can, with translation, understand what the primary information was, not some my bête noire, not some PowerPoint distillation of it. So I enjoy that, but I don't know how the speed of that relates, in a sense, to communicating. It isn't really speed, it's the ability to talk to a person without using long words if you can use short ones. And that's something that we have to learn to do.
I'm going to open up the questions to the audience in just a moment, but what if you had a student come to you today or tomorrow and they said, what's the best piece of advice you can give me as I'm beginning my training in science? What would you tell them?
Oh, I would say, look around for something that you enjoy doing. That's the primary thing. If you don't enjoy it, you won't ever do very well. And I say to students that, and I use my own career as an example, I say my PhD was involved, wasn't originally set out to do this, but it involved designing and building a relatively complicated piece of apparatus to measure osmotic pressures. And it was a good piece of machinery in the end, apparatus, not machinery, and it was very precise, and so precise that I had to interrupt my theoretical line to let my points show, because they would be covered by the line. And I pointed out that nobody ever quoted that paper. And nobody ever used that machine. I didn't use it again. And so what was it? What did it achieve? Well, in doing it, I learned how to do science. And that's what it was about. It didn't matter what it was, really. I'd learned how to do science. It didn't have any contribution to the future of mankind or womankind. But I enjoyed doing it. I had a very good time. And later on, I wouldn't be doing experimental science if I didn't enjoy it. I go to the lab at the weekends. I don't go to work. I go to play. I mean, I get paid for playing. So if you're a student and you find yourself doing something that you don't like, go to your advisor and ask for a change. If you don't like looking down the microscope, you shouldn't be looking down the microscope 2 or 3 hours a day. If you don't like handling mice, you shouldn't be working with mice. You may have to work with mice that you don't really, which isn't your favorite part of the day. But anyway, what I'm generally saying is find something that you like doing every day. Not every day, but every day. And then if your advisor won't help you change, there is another solution. Change your advisor. I've said that before, but I mean it seriously. That's the single most important thing, is to find something that you enjoy doing and do it well.
And I'm going to share something you told me before we came up here and started this session. I'd ask Oliver, what was one of the funnest things or one of the biggest benefits of getting the Nobel Prize here on this campus? And would you like to tell him what it was?
Well, the funnest.
Right.
You said the funnest.
That's funnest.
Funnest.
Okay.
What was the most fun? Well, it was when our old Chancellor got up at the, I think it was faculty day. He'd introduced me to the faculty earlier on, and then later on in the course of he sort of deadpan and got up and said, now I'm going to take a privilege which chancellors can have, and I'm going to say that Smithies has a free parking place for the rest of his life. I think that was the funniest thing, because I did this because it's actually very useful. I know where I can go. Occasionally I have to take a piece of paper out of my, we made a few cards of this that says, you have parked in a place that is reserved for somebody else. Would you please move your car? We've had to use that a few times, but not very often actually. It's honoured very well, but that's the funnest thing that happened. And then I got to go to the Final Four last year, because but that was another story I should tell you, since we're telling stories. He called me up about a couple of weeks later after this incident, and then said, but then he called me Oliver. He said, Oliver, I'd like to ask you a favour of you. And I said, oh, what's that? I said, I'll do my best, Chancellor. He said, well, I'd like you to have your photograph taken in a UNC basketball jersey. I said, what? And he said, yes, I want to have an ad in the New York Times showing that UNC is not only good at basketball. and so eventually got this photograph, and some of you have probably seen it, with me holding a basketball. I never held a basketball in my life before. and they even changed the number to 50. And those of you who know basketball know Tyler Hansborough's number is 50. Anyway, it's a pretty glorious thing. Not that part of it. But, well, I said, Chancellor, you know, if I'm going to do that, don't you think I ought to go to the game? And he said, oh, yes, I think we can manage that. And I said, well, it'd be nice if my wife came with me. He said, well, we can do that too. And then I'm really rolling now. And I said, how am I going to get there? So we got on the athletics plane to go there, and we had a good time. Unfortunately, we lost on the first game, as too many of you know. Not going to happen this time. I'm not going this time either, so I won't be a jinx.
So those of you who did not know Professor Smithies before today, you can see that he's someone that's very approachable and certainly is willing to discuss anything. So let me open it up to questions, and I guess we want to make sure that when we do that you speak into the microphone. So who has a question for our distinguished guests? Yes, in the back in the field. And if you could also identify who you are and if you're a student or faculty member.
My name is Anna Goldstein. I'm a second-year graduate student in chemistry.
Louder.
I'm a second-year graduate student in chemistry, and many of the papers and journals that I look up on SciFinder relating to my research end up being in Chinese or Russian or some other language that I don't speak. And I think previously that might have been the case with French or German. So because communication and sharing is so important, I'm wondering what your thoughts are on the common language of science.
Well, when I was a chemistry student, I did study chemistry as well as physiology, and you had to learn German and pass a German exam, because at that time most, at least of the organic chemistry literature was in German, and one did it. It was a necessary thing. I think the matter-of-fact situation is now that English is the scientific language, and so that's what's happening. Nearly all of the important work is published in English or translated very quickly. So I don't, in a way, I don't know that I agree with you about a lot of them being in other languages. I've used SciFinder, and I don't find all that many, but it maybe are different things that we look at in that respect. But it just happens to be the way life is, as it were, or how the world is, that the language of universal usage changes with power structures. So it was Latin. I suppose at one time it might have been Greek, but it was Latin for a long time, and then you socially were inept if you didn't talk French, and that goes back, of course, to the Norman conquest, because the Normans conquered England and brought with them the French language, which we see still in our language now. It's marvelous, I always think, to realize why we talk about beef and mutton. And we talk about beef because bœuf is the French for cow, and mouton is the French for a sheep. And so when it was on the table, the aristocracy only talked about cow and pig, pork, and sheep in their language, which was French. So languages go with power, and I don't know how long we'll last in English.
It's open for questions. I think we have one here. Actually, here in the second row, sorry.
Diane Ward, faculty nutrition. Over your career, I'm sure you've seen some groundbreaking discoveries in science. What do you think are the major groundbreaking discoveries that you've seen, and what do you see coming ahead?
Well, you know, the groundbreaking ones just keep coming, don't they? I mean, I mentioned Watson Crick, but you can go back almost a generation, in fact, at least a generation. When I was a student, I remember our professor coming in one day and very excited and say, it's just been discovered that DNA is the genetic material. See, it wasn't known that DNA was the genetic material. So that was a groundbreaking thing. Came out, and then the Watson Crick thing was very groundbreaking. I remember the first time it was possible to sequence DNA, and that was enormously exciting, because I went to this meeting, and a young graduate student, Nancy Maisel, gave the talk, and she got up and she started on the blackboard and she wrote down 60 letters, and that was the sequence of DNA from the bacterium E. coli between the gene she was studying, which was beta-galactosidase, which was a protein that makes the protein enzyme, and the controlling sequence, which was upstream, the so-called operator. And this sequence was, she just wrote it down. Of course, we couldn't tell whether she'd written the real one down. She could have written 60 letters of any sort, and we wouldn't have known. But she wrote that down. It was very exciting, and I thought, now I want to do that for a human gene, for 2 human genes. And that got me started in doing work with DNA and sequencing. Of course, I had no idea how difficult the problem was, or I might not have done it. It was much more difficult, and it didn't mean anything when you got it. You didn't understand what you got, you see. So, but there was a world-breaking thing. And if I could tell you what the future was, I would be doing it.
I have a question, if I may, kind of a follow-up to the earlier one. How has collaboration in science changed over the course of your career? And does the availability of so much more information online have anything to do with that?
Oh, I don't think collaboration in science has changed. I think it's very good in general. I think people collaborate readily and easily most of the time. If you get somebody comes to you and says, for example, I'd like to use something that you've made, and if you've already made it and published it, it's your understood obligation to give it without return. In other words, you don't get authorship or anything. And we do that all the time. If you haven't yet published it, then there is an implicit agreement, which is, it's better stated explicitly, to collaborate and publish together. But the collaborations are always enjoyable if you remember the golden rule, which is when you think about the collaboration, you don't think about yourself. You think about your collaborator. You always think about what is in it for you, looking at the collaborator. Because it will take care of yourself, all right, but if you think about what's in it for your collaborator, you will have a happy collaboration. And most of mine have been lifelong and most enjoyable. I had a lovely one in relation to the genes which affect blood pressure and have other side effects. And this scientist in France, Francois, oh yeah, Francois Alongelat. He wrote to me and said, we'd like to have your mice to do an experiment, because I'd made some mice in which this particular gene that he was interested in varied in the level of expression. So I had mice that had less than normal, or more than normal. And I sent these mice to him, and he did work with them, and we published a paper together, which led to some interesting things. But I never met him. And then I had to give a talk in New York, and I knew he was coming to the meeting, but I got up and I gave my talk, and I got to the part where, and I have this marvelous collaboration with this Francois Alongelat, but I've never met him, and a guy at the back of the room got up and me. And then later, when we visited France, and we and I visited France, he turns out he's lived all his life in Paris. And so he took us on a self-driven tour of Paris in the evening. He knew how to get through all the traffic and all the places. It was a marvelous ride.
That's almost as good as the NCAA's.
That's right. So collaborations have been a joy for me. I've had many, and I don't think there's a single one that's ended up in a problem. There's one that I missed that I always regret. There's one where I was given some samples of serum, and in the early days, and I didn't think that, and I did a lot of work with them, and then contacted other people and worked out some genetic thing. But the person who first given me that sample, I should have had his name on my paper. He should have been a collaborator, and I missed it. And I wrote to him, when he wrote to me when I got the Nobel Prize, and I wrote to him saying, now I can contact you and I can tell you how how sorry I am that I didn't include you in that paper, because that's one of the few ones that I can remember not doing what I would have liked. I didn't realize it, you know, he should have said. But that's collaboration. It's a joy as a collaboration. I don't think it's changed at all since the explosion of things.
But do you think the internet connectivity we have has made it somewhat easier to communicate with scientists in other places?
I don't use the internet to communicate. You're asking the wrong
I know
person.
that.
I don't even need do email. I never did mail either. A mail would come and I would open it and then think I might reply to it one day. And I remember coming across the one when I was in the early days of starch gel electrophoresis, when somebody wrote to me and I came across this letter, and in it he'd said, I'm hoping to come and visit you, and that you will show me various things. And that was a week after he said he was going to come, and I'd never replied. And so I thought, oh dear. And so I wrote him a nice, polite letter saying that I was sorry that I hadn't replied to his letter, and please do feel that you can come, you know. And he wrote back and said, but I came. And you showed me everything I wanted to see. Boom. There's a couple of other, there's some correspondence that I wish I'd still got the copy of. There was one in the early days of when we didn't understand that you have to be very careful when studying families about what information you give back to the family, because sometimes it can be embarrassing for the family. And there was one family where the blood groups showed that there was a case of non-paternity, almost certainly, and we didn't want to upset the family, and so we wrote to the person who had done the blood groups for us and said, oh, his name was Bruce Chan. Bruce, for goodness sake, just help us to respond to this question without upsetting the family. And he wrote back a long, complicated letter, and there was no Xeroxing available, of course, at that time. It was a carbon copy I had with a typewriter with a carbon, and highly involved about sometimes blood groups don't show the way they're really inherited, etc., etc., etc. And he sent me a copy. At the bottom, in his handwriting, he'd written, and you know, Oliver, it might even be true.
A question in the back.
Right.
Hi, my name is Ijo Dong, 30-year graduate student from School of Pharmacy. I have a question about the grant. We know faculty member has to apply for a grant to do research. Some faculty member like to publish more papers to apply for more grants, and some faculty like to do real science they think and publish better papers. Do you have any comments about that? Thank you.
Well, I think I probably belong to the second group, and they don't get funded as easily as the first group. I don't think there is any, unfortunately, there's no simple answer to that question. I think you have to do what you have to do, as it were. And I can't write trivial papers. I find it, they're not enjoyable, and so I tend to publish relatively infrequently. And I don't do better at getting grants than most other people. I don't think I mean, I have one that I was telling Tony about that I applied for about 2.5 years ago with my kidney work. I had this glorious hypothesis, you see, and I have applied for a grant that's called an R21, which is where you can try something that's way out and you don't have to have preliminary data or anything. So I sent this in, and it got turned around, no preliminary data. You aren't supposed to have preliminary data for that, so that's what happened to that one. So then I wrote, I got preliminary data, and now this is after I got the Nobel Prize, and I sent it in with answering all the questions with the preliminary data, and now they didn't like the hypothesis. So I didn't get it either way. So I'm afraid it happens to all of us. Now I don't know, there's no answer that's simple. you just do the best you can and you do the way you want to do science. And it's better to write good papers infrequently than poor papers frequently. But you have to have some sort of compromise in order to survive.
Excuse me. I don't mean this disrespectfully, but I'm wondering if the knockout gene business that you've been involved with and so successful in is kind of coming to an end, or is going to be over within the next 10 years or so.
Yeah, I would hope it would come to an end, in a sense that people will find better ways of doing things, because that's what science is. It always progresses. And I think it's had rather a long life. I'm surprised, really, because we published our first paper showing that it was possible in 1985, and so that's 20 years ago, and the first animals in about 1989, so that's still 19 years ago, isn't it, or whatever, and still people are doing it, and in fact but I think it's much more advanced than knocking out. I like to make the comparison that we all differ. We just look around and you can see we're all different, and that's exciting and interesting. And we have different susceptibilities to various conditions, especially as we get older, they show more. But these aren't due to knockout of anything. Because if they were knockout, they would be relatively simple to discover, because they will be inherited in a simple manner.